So welcome back to the Jian course day 3, Wednesday. So today's topic is first of all, today's first topic is Professor Taimoor Khan selected topics of the WPT system, etc. It includes a machine learning approach. It's very interesting topic. So please start your talk.
Good morning, one and all. The topic for this lecture is selected topics on WPT systems. A glimpse of that one I have already discussed in the last lecture, that was power combiner as well as power splitters. Then, but intentionally I have incorporated, because in the entire Gyan course we are not touching a single lecture on that machine learning approach for modeling and optimization of RFEH or WPT systems. That's why a glimpse of that one will be discussed here in this lecture. Let's start the things that these are different sources which may be used for as an ambient source, and based on that one, the two types of power combining will be there. One is direct antenna output is combined and then rectification will take place. That is RF combining. Okay, uh, this will be having a specific reason where the ambient energy is very small. Then you combine all ambient energy of different sources, then that output of that combiner will be sufficient to feed or to excite the rectifier part. That is the themes behind that one. And in another way, that individual antenna output is connecting to the rectifier through matching network, then second antenna, third, and combining we are taking place at the output of rectification. That is, if ambient environment is having sufficient energy corresponding to each source, then directly it is rectified. Then finally, after rectification, it is combined to create the larger amount of energy or that power. Here, moving ahead, that same scenario means power combiner with power management unit. It is a standard unit available with different names in the market that we can use directly or we can design ourselves also. That is equivalent to that voltage regulator kind of things, because these source energy will be varying in atmosphere, and finally means after taking that each one, then this combiner output is fed to that PMU, and finally here at these points you will get that regulated or stabilized output from the PMU. Now coming to that power splitting approach, because like in traditional micro engineering, we also discussed that one power divider as well as power combiner. Based on that, my your waveguide also. But here that I am taking in the reference of SWIPT, where you are having a source which is giving both information and energy to the receiver side. Then finally means it is happening that receiver may have a specific environment of sensors or IoT devices. Then the power requirement of these devices is very small. That's why in addition to sending the information, we send the power also to excite that one. Then there will be no requirement of having the battery inside this IoT network. That is the themes behind using. We are sending both information as well as energy from a dedicated source to the that one. Here you can see that three different cases: antenna switching, then time switching, as well as power switching. Okay, the same concept means it is coming to that receiver side. For two different kind of decoding will be taking place. One is for information decoding, second one is for energy decoding or energy harvested energy decoding, and finally means this will go to the power supply unit of that receiver, and this will go for the information processing. to that way. Then in that way means two different kinds of switching, that is another way. Then finally means it may be a single switch which like multiplexing kinds of thing. It will for a certain period of time it is connecting to this one to this day, as well as to have a certain power splitting concept. The detail of that one has not been included here, just an overview to that. Means because today in this lecture I will be going to focus only that third part, that is machine learning approach for especially for different components used in the RFEH or WPT system. That the machine learning approach for modeling as well as optimization of key components of a rectangular system. So what key component we have studied, that is antenna as well as rectifier primarily. That impedance matching network will also be taking place. Then depending upon the scenario, we can apply machine learning for antenna, machine learning for rectifier also, machine learning for complete rectangular system, and machine learning for that in other components also. Let us take an example of some traditional form of antennas what we are having in our environment. What common thing in all these things, that each antenna is having a different functions, but common thing that all are electromagnetically coupled. The phenomena of radiating in all these cases or receiving the energy in all these cases is common. But here the purpose of using this antenna is different. Here the purpose of this using this antenna is different. Here Yagi antenna, Yagiuda antenna, that is different. This dish, mobile phone, this kind of antenna. And these are the some futuristic or present smartphone concept, this one, and that is the future one, fully transparent, that we will see in the near future. Here you cannot see where is the antenna because it is inside that printed circuit board. In earlier first or second generation of mobile phone, it was coming out from the body of that mobile phone. Okay, the idea behind taking all these different varieties of antenna, that's to correlate that one common thing is there, that is that all are electromagnetically coupled. Okay, like used for converting the electrical energy into electromagnetic waves or electromagnetic energy into back electrical waves in case of receiver, and in case of transmitter electrical to EM waves into the space. Then another variety of that one, because in last lectures we have discussed some like correlates between the biomedical and healthcare, different scenario, that implantable pacemakers, implantable chips, and different wristband and all other scenarios for different cases that we can see, all are having at least an antenna. Rest of the things you may not take seriously at this moment, but all these applications are having at least an antenna. The modeling, the optimization of antenna in this application domain as well as in the generic classification of antenna, that will be different, because machine learning is not having a difference that for what application you are going to model that antenna. It will take your parameters as an input and will predict the response accordingly what algorithm you are using for different machine learning scenarios or different applications. Let's conclude this two slides, this one to earlier one, in a simple way, that we are having a simple form of printed antennas. The concept of that one was very old, that in the year of 1953 by Deschamps, and the first prototype was fabricated by Howells and Munson in 1970s. There is a huge gap of around 17 years because there was no fabrication facilities that time available in during the 1970s. It could possible to fabricate that one. Okay, that is means all those kinds of antenna that you may presume that it is having a radiator, it is having a ground plane and substrate thickness, substrate permittivity. This is the simplest way to take that one in the form of to correlate the previous different scenarios of antenna cases. Now, as far as like because uh, in my group, apart from that RFEH and WPT, we are also working in the modeling and optimization of antenna related problem or electromagnetic problem, that is classified into three different categories. One is like antenna modeling, maybe analysis modeling, synthesis modeling, and the third is specific case for interference rejection in ultra wideband antennas. Then maybe second one is periodic structures, not antenna, that is structure modeling, that is EBG structure. We have some work on EBG structure modeling, frequency selective structure modeling, frequency selective surface modeling, as well as meta surface modeling using machine learning technique. And coming to that optimization is defined into two different categories. One is that specific geometry optimization, and second one is optimizing the methods for that way. So then two different categories may be further extended. Coming to that artificial intelligence, it may be ANN, fuzzy, evolutionary algorithms, swarm algorithms. Then combination of these may also be processed. We have some published work in different classification of these combinations, and applications may be a single element based or arrays of elements based. Now you are not going diverted to that one. That single element may be single antenna used for WPT or RFEH. Okay, then arrays of elements may also be used in the form of antenna array or in the form of MIMO or some other configuration to that way. Now, just see, in case of antenna analysis, you need to give the geometrical parameters, different dimensions of that geometry, and to predict the electrical performance parameter, maybe gain, bandwidth, axial ratio, or radiation efficiency, antenna efficiency, something like that. Only electrical performance parameter. That part is basically comes under the banner of that analysis modeling, or that antenna analysis means where the geometrical parameters are given to you and you need to predict the electrical performance. Now take it reverse. Performance is given to you that I need to design an antenna with certain bandwidth, certain amount of gain, and you need to drive the geometry of that one. That will comes under the reverse way, that is antenna synthesis. You need to remember that in analysis, prediction of electrical parameters will be there at the given geometrical parameter. In case of synthesis, that prediction of geometrical parameters will be there with the given electrical parameters. Now, the traditional way of modeling of antennas available in the literature, that is transmission line model, multiport network, cavity model also. Okay, that is analytical methods. Then numerical methods say the method of moment, finite element method, then spectral domain technique, finite difference time domain. Each one is having specific applications, specific advantage as well as the drawbacks, because we need to drive the need of machine learning incorporation in the existing modeling approach. That's why some problems based on that analytical methods are highlighted here. That is, the simple methods are simple, but based on physical assumption and applicable only for regular geometries, not any kind of a twist in the geometry. Then it will be difficult to drive the this mathematics using these three techniques. Coming to that numerical method, applicable to irregular geometries also may be possible to apply for regular as well as to irregular. Comparatively good results. Okay, complexity in integral, because entire mathematics is in the form of integral form. Okay, and we as a human being are comfortable in the differential rather than to the integral form. Integral equations are very difficult to solve rather than to the differentiation. And now in new solutions for every small variation, if slight changes is there in any parameter, then the entire mathematics will be changed. Okay, now conclusion for that one, that the obligation for having a new solution for every minor change in the geometry in numerical method, what is mentioned here, and the problems associated with the thickness of substrate, because it is for thin substrate, because several parameters we need to optimize while considering the thick substrate, then leads to the complexity as well as the processing cost. What should be the alternative to this one? Okay, then one need is required. That need will be fulfilled in after incorporating the machine learning approach. Another problem that no mathematical model exists except measurement. There are several cases. Nowadays simulation environment is available. You recall 50 years ago there was no concept of simulation model. The concept you need to drive mathematically, you need to do the fabrication measurement, and it was quite expensive process. Okay, because substrate cost and fabrication cost, measurement cost will come into the picture. In that way, means we need to go towards the other challenges, that closed form solution does not exist, and only in the simulation environment we use the trial and error method. What geometry you are optimizing, you are taking at the final values of geometry, it is not the optimized version. It is your trial and error method. And another problem that the performance of your simulated geometry is quite far away to the real one, because third one is in the optimization, that convergence problems will come into the picture. If geometry is complicated, then it will take large amount of resources for getting the optimized versions. And to overcome all these challenges, not 100%, certain up to certain level as well as to the previous one, then we need to enter into that machine learning approach, especially for electromagnetic problems. Then the very good reference is QJ Chang and KC Gupta, neural network for RF and microwave designs. It was a very good reference. You may refer to that one. Now coming to that, in this way, I'll be going to focus only that neural network approach with applications as a single element. Okay, because due to time constant, the idea I need to explore only within a limited period of 1 hour. That's why here I will pick up only that neural network approach along with single element antennas and analysis and synthesis, no optimization, no array of antenna element. Further it may be explored to that way. Certain advantages with ANN, that is uh, parallel nature, parallel processing, that is the uniqueness. Each and everything means the task is divided into the equally to all the neurons used in that model. And second one is it is adaptive in nature, that all changes will be easily adapted in terms of optimized weights and bias values. And next one is the nonlinear characteristic, because in hidden layer, what activation function you are using, that is highly nonlinear, and that nonlinearity will correlate to the problems in the electromagnetic domains. Then this advantage also, that unbelievable growth both in terms of novel architecture as well as new applications are coming day by day. Neural network or ANN modelings of antenna problems. Now just see two different phases of ANN. First is training. What we do in the training, that you are having a certain data sets created by the simulations or some other means. Then you need to define a structure of that model where inputs are presented and corresponding response are presented. In the sense, this red box equivalent to a small kid of 3 years old or 4 years old, when his or her mother is telling that 2 plus 2 answer is 4. One side inputs are fed to 2 plus 2, answer is also told by the mother 4. Then that kid starts to memorize. Whenever mother will say 2 plus 2, I need to react 4. There is no processing of 2 plus 2 equal to 4 in his or her brain. It is only just giving a input one pattern. Same patterns will be followed to 3 plus 3 equal to 6, then 4 plus 4, something like that. Then if you are having certain huge number of patterns and corresponding to response, then equivalent to what we are doing, it is having a structure of certain hidden layer, certain input layer, output layer with certain activation function. Then what changes you are applying in the input to desired response, that changes are adopted in terms of weights. At each steps, that weights and bias metrics are changing. And finally, when that you are able to give all sets of inputs and output, then what the model will be trained, in the sense that some knowledge will be gained. Okay, knowledge in the gain means same examples. When that small baby is going to the first time for admission, then some sort of questions will come from that school side, that you recite a poem or 2 plus 2 equal to how much, something, then automatically that answer will come before completion of the questions, because it is permanently fed to or done the lot of practice on that patterns. Okay, then what knowledge we have gained, that knowledge will be retained in terms of weights and bias values. Okay, that is in this way, that knowledge we are extracting from that model, and now we are creating a model, different model. Okay, structure of this model will be same to that training model, dimensionality of input pattern, response will also be changed. It is not going to change. Okay, then ultimately we apply a new pattern to predict the response. Then how rigorously you have optimized this one. Okay, then ultimately it is dependent on that, finally means how accurately you are getting the response from the trained model. Okay, if it is very simple structure, only you have not spent the time during the training, then finally the response will be very far from the actual response. Okay, training is very rigorous. Like in during your 4-year BTech program, each semester is giving a certain amount of training to make you perfect engineer by the end of 8 semesters. That is happening. Then each semester is having, in total 4-year programs, might be you are having 40 subjects training. Once you become that one, then after graduating, you are applying that knowledge in higher studies, you are applying that knowledge in some research institute or some jobs may be research related job, maybe marketing or some other ways. Ultimately, what knowledge you have gained during that training period of that one, lifelong you will be tested based on that knowledge. That is ultimately the basic themes of applying the training as well as the testing to that way. Now let us take an example of an arbitrary m dimensional input, n dimensional hidden layer, and p number of p neurons in the output layer. Okay, that is an arbitrary structure. It may be 2 cross 3 cross 5, something like that. Then the data flow is unidirectional, distributed and parallel, processed in parallel. Unidirectional means from left to right data will be processed. It is distributed, that applied data at this one neuron will be distributed to all neurons, and processed in parallel. All neurons are processing the data coming in parallel. That is, apply m dimensional excitation to predict the p dimensional response, because the dimensionality of output layers will be same to the dimensionality of predicted response. Same thing, dimensionality of input will be the dimensionality of input world or that input layer. Okay, now we need to give certain, because the size of this matrix will be m cross n. If you have an idea of linear algebra, the size of this one will be m cross n. That ultimately we need to insert some weights within this matrix m cross n. Size of this w1 will be m cross n. Then that random initial values you need to give, not 0 0. If you are making 0, then everything will be 0. Non-zero, it may be, because certain algorithms, certain ways for taking that one, it may be -1 to +1, it may be 0 to 1, it may be -0.5 to +0.5. Okay, then in the same order you need to assign some random values for that input matrix, and same thing will be happening to this bias matrix also. Then output matrix, W matrix, and as well as to B2 matrix. After assigning this value, you will calculate simple multiplication and addition process. No need to apply the genius way of mathematics to that one. Simple multiplication, addition, and passing through the activation. Once you calculate this output, then it is to be compared to the reference. What should be the value of this corresponding? Suppose you have given length of patch equal to, suppose, the width of patch epsilon r, relative permittivity of that geometry. Then what corresponding should be the resonant frequency of that values, that you know it very well with the reference of Balanis chapter or that 14th chapter of that Balanis book, Antenna Theory. Okay, then you know that for this particular combination I should have the calculated value nearby to that 2.4 gigahertz, 2.45 or 5.8 gigahertz. Okay, if this calculated output is nearby to that one, but certainly it will not be, then there will be some difference, error matrix will come into the picture. After calculating this error, you need to optimize this matrix first. Now calculate the changes here, difference of calculated output and reference output, the difference amount, weight matrix, weight factors will come into the picture. Then accordingly, the bias B2 matrix and W2 matrix will be optimized in first step. Then it will come to the next one, W1 and W2. Now, after calculation one time, after that you need to update the W1, W2, B1, B2 matrix. Now, before you need to apply the second set of excitation. to get the response. And finally, you will predict that whether this error in second step is lower than to that one or upper than to that, and accordingly that algorithm will upgrade to that one, that the same amount of error is to be propagated backward to forward side. Just see that one, data is flowing from left to right. In this geometry, data is flowing from left to right, but error is propagating from right to left. That's why the term back propagation algorithm, that what we use in the machine learning, comes into the picture. Okay, now these are few steps for calculating this one in the reference of MATLAB, or it may be in the Python or some other platform. That is start, then load the training data, data normalization, because real problems may not always be available in the form of what, uh, zeros and ones. Okay, real, because we need to play as a current, voltage and power something, that if it is there, then ultimately you need to normalize that way, because the machine learning techniques gives the effective outcome for normalized patterns applied to that any algorithm. Then ultimately select the parameter, number of hidden layer, number of hidden neurons, activation function, learning algorithm, then initialization of weights and biases according to selected architecture of that model, then train the model, and then if it is perfectly trained, yes, then you need to retrieve the weights. If it is not perfectly trained, then the repeat into that one, you need to change the structure of that way, until unless you get the errors as what target you have set during the training, that I need to train the model with a mean square value of this particular amount. Accordingly, if that loop will continue until unless you get the that set amount of errors, in terms of that weights, updated weights and biases will come into the picture. Now after retrieving these weights and biases, you need to take that one into that other part, that is the testing one, that load testing data into MATLAB, data normalization, then it will be the multiplication with W optimized matrix, then add with bias values, then ultimately activation function, then finally predict the testing performance. Here the performance should be more or less what error, what parameters you have set during the training to that way. That is an idea of creating that ANN model for any problems related to antenna or microwave in the MATLAB, or it may be an other platform also. Now coming to that few steps, you can just read that one without saying anything. These are same steps what I have told, discussed in the previous flow diagram. Create a neural network model, define excitation metrics and the response, initial weights and bias values, then define some parameter like mean square error, number of attrition, etc. Observe the convergence of the network, whether it is converging or not. Then if it is converging, then well and good. If it is not converging, then you need to make the change in the weights and bias values, then retrieve the weights and biases. If the model is converged, then remove 25%, not 25, it may be 20%, it may be 30%. And in one example, I'll show you that we are able to do that modeling with a less amount of training data sets also. Put the retrieved weights and bias in training, train the model with roughly 75% and test the model for the remaining this way. Here, four different cases, four different example I'll try to cover in this way if time permits. First one means analysis modeling using ANN, synthesis using ANN. Okay. Then third one, approach one means that is traditional approach. It is more advanced knowledge based neural network modeling. Okay. Then again two examples, analysis using KBNN, synthesis using KBNN. Then two examples in traditional approach, two example in advanced approach. One is on analysis, another one is in synthesis. Might be same design, same geometry for analysis, same geometry for synthesis. It may also happen, or it may be different to that way, because we need to focus only that approach, not on the example. Okay, just see that one, example one. That is what was that one? Interference rejection in UWB antenna, that is not relevant to that RF and WH, but that quickly we can move ahead with that one. That 3.1 to 10.6 gigahertz is the UWB band, but in that when it came into picture in 2002, then several other technology are also existing. Then there is an overlapping nature of these ones. Okay, when you are using that 3.1 to 10.6 gigahertz band as a UWB, at that time the interference of these overlapping bands should be considered properly. Okay, that's why the task in this example is to remove the interference of these bands only, that is 3, 5, total 7 bands which are overlapping to that UWB1. Then for that one is geometry, then second step, third step, fourth step. Then here you are getting 2.6 to 10.6 gigahertz UWB. Here interference band, while incorporating this U-shaped slot, one interference band or rejection band is appearing 3.7 to 4.2 gigahertz. Antenna 2, then it is 3.3 to 3.7 gigahertz. Then antenna 4, it is to this way. Then ultimately here between these two slots, a gap of 0.6 mm is maintained between the slot 1 to 3, because lesser than to that one is not feasible because of fabrication limitations. Okay, then here response, you can see that one, that is the antenna 1 response. Then antenna 2, this notch is coming, this particular point will reject that specific band, that is 3.9 gigahertz frequency. Okay, this point, and here you can see that along with that f1 f2 lower and upper cutoff frequency, you are getting two notch fn1 and fn2, here in three notch fn1 fn2 fn3. Okay, now while changing the dimensions, like these are the total 15 the geometrical parameters, and the response is this one, means we need to develop a model which take 15 dimensional input to predict that 5 dimensional response. Okay, in that way the total 1195 patterns are generated out of 956 patterns used during training and 239 during testing. Two models, model 1 and model 2, just see that one is having single hidden layer, second one is having two hidden layers. Okay, then how the performance is changing with different number of neurons in the hidden layers in two different cases, that we'll see later. Total 7 algorithm, 1 2 3 4 5 6 7 algorithms are used or tested. In that way the criteria of generating patterns is something like that, that LP dimension is changed between 12 to 17 mm with an internal steps of 0.025. Like first step is 12, second is 12.025, 12.050, something like that. Then same pattern you are applying for antenna 1, 2, 3 and 4. These are the total number of data sets generated in each case, and finally total, if you combine that one, it becomes 1195. That is the model. N dimensional, n means what here, that is 15, m means 5 here, because we need to predict 5 dimensional response for the given n dimension 15 dimensional excitation. Okay, then this mathematics we can skip here, no need to go into that way. Directly model 1, that is hidden input neuron 15, output neuron fixed, it will map to the input excitation as well as to the response, no need to change. Change is only that hidden neurons, that is single layer with 10 hidden neurons. Then how, then second model, two hidden layer with 10 neurons. Just see the performance what is happening. For model 1, that model 1 means single hidden neurons, that number of neurons 5 6 7 8 9 10. Just see the errors, that is during training, it is that we are getting at r equal to 10. When you are considering 10 neurons in single hidden layer, then you are getting the least error. Okay, then for model 2, then r equal to 10, t equal to 10, that is number of neurons in first hidden layer as well as second hidden layer, both are 10 to get the least possible error. So that way other combinations you can see that how much amount of error we are getting to this way. Then number of like different algorithms, variations with that optimized structures, then hyperbolic tangent activation functions is giving the least error. Here Elliott activation function is giving the least error, LM algorithm and Bayesian regulations algorithm is giving the least possible error. Then final optimized model what we are having 15 10 10 5, mean square error during training testing as well as to that validation, that is the least possible for that one. And here fabricated measurement and that simulated values, measured values, then errors in the two models, then final comparison that you can see. Coming to that second one, synthesis of model, that will take the reverse approach. Electrical performance will be given, you need to predict the geometrical matrix. Okay, it may be different. Just come to that directly geometry. This is that geometry. Okay, that this we need to have certain electrical performance, maybe gain, maybe bandwidth, efficiencies, etc. And we need to predict the geometry in terms of this one rectangle patch with some slots at the center of that way. Then the slot is divided into 4 different ways, that is asymmetrical cross section. All these are not symmetrical, that x1 does not equal to y1 and x2 does not equal to y2. Symmetrical means you will have a square shape. If once vertical portion you are considering, that it will be considered as a transfer slot. This one you will consider as a longitudinal slot. Okay, that slot may be different in your different antenna related to WPT or RFEH, because ultimately that idea is more important rather than to the specific geometry. Then dimensions are changing, x1, y1, x2, y2 within 1 mm to 50 mm, and the t is the thickness. Okay, that is changing 1 mm to 10 mm. Then here different set of parameters while considering 4 different cases, 490 in each, that is generated. And finally coming to that model, DR means dual resonance, dual frequency gain, dual frequency directivity, dual frequency antenna efficiency, dual frequency radiation efficiency. Okay, then you need to predict the slot size as well as the air gap. You are having, your requirement is to have certain amount of gain that is given here. Okay, that you need to drive that geometry. For that one you are doing the machine learning modeling. Okay, then certain weights and biases that we have optimized between -1 to +1, mean square error, learning rate, momentum coefficient, algorithms, then pattern 1000 plus for training and 350 for testing. Coming to that performance that you can see here during training and during testing with the 7 different algorithms, the last one is giving the best performance in terms of error as well as in terms of training time and the number of iterations required. Okay, now comparison simulated predictive value parameters, because our task is to predict the dimension x1, y1, x2, y2 as well as the air gap between the radiator to the ground plane. Then the simulated values and predicted by the neural model that we are getting here. Coming to that performance of proposed approach, because more than 1000 patterns cannot be plotted in the form of 2-dimensional pattern on a paper. That's why a different approach is computed for observing the performance, whether the error is uniformly distributed of all the patterns or not. For that one, means we have calculated for 5 different parameters values as well as the standard deviation, then coefficient of variations. If it is defined as the ratio of standard deviation to the mean value, COV closer to 0 represents the greater uniformity, nearby to 0. Okay, if it is nearby to 1, then there is a variability that all the error points are not uniformly distributed. Then ultimately it is calculated that coefficient of variation, all values are nearer to 0 rather than to 1. Although all are different but nearer to 0 rather than to 1. That's why we may predict that errors on more than 1000 patterns is uniformly distributed. Then the simulated frequency range, that is simulation time and memory space required, that is simulation time, that is 1 hour 53 minutes per structure, and the memory RAM required 36 MB of that systems. Then how that performance is changed, testing time performance, that is few lines coding that you can create in MATLAB, CPU with the help of CPU time, and ultimately required memory space, that is a few KB during the testing, 1.40 KB for testing and 29 KB for training, and it was very large amount of memory required, that is 36 MB in case of that simulation one. but computed testing time is very small, that is 53 milliseconds. Once the model is trained, then you will get very quickly the response from the parameter. Then this is the fabricated setup as well as the fabrication one. Then I can skip it quickly because it is just mapping of simulated and measurement performance for different parameters. Then comparison of dual resonance, that is measured values, simulated values in case of longitudinal slot, transfer slot as well as the cross slots. Then bandwidth is changed bit. Simulated bandwidth was 55.5 megahertz and measured it is 250 megahertz due to some tolerances usually occurs during the testing as well as the fabrication of the prototype. Dual resonance without slot 2.0, with cross slot it is that one. It means you are getting the compactness in the structure, that is both the frequencies are lowered by 13%, that is creating a compactness of 35%. Here that's ultimately gain and directivity performance corresponding to these points. This was the first resonance and second resonance. Then antenna efficiency. Coming to the main means what problems was there in earlier two example that we need to highlight, and it's remedial in the knowledge based neural network. That is, the neural model I discussed in the previous two cases may not be very reliable without having adequate number of training patterns, because you need to have huge patterns required for training of those models. And sometimes if the geometry is very complicated, then each structure may have more than a hours, and you need to generate such thousands of structures for creating the sufficient number of data patterns. In that way, then generating large amount of training patterns is time consuming and expensive. Okay, if this task is assigned in the first year of PhD, maybe after the first year he or she may try to leave that PhD program because it is very time consuming process. Reliability is not guaranteed and is most expensive, very poor. In case of extrapolation region, I'll tell you what is that extrapolation or interpolation regions in case of machine learning. Now, the remedial of all this is to incorporate that additional knowledge in the existing model, what we have discussed in the model 1 and example 1 and example 2. Same approach, but you need to incorporate some additional knowledge. That additional knowledge will come by different ways that I'll discuss here. The prior knowledge contains some information about the behavior of that problem, about the behavior of the problem, certain points that you need to suppose reach to NIT point. Certain points are given that you leave, take right turn, then after moving ahead you will have some like fair price shop point. After that you need to take the another turn. No need to define the entire path. Certain points which is reference point that you have given to that model, and finally that additional knowledge what you are incorporating to that way, rather than to giving a certain instruction, go to NIT point and bring this one. It will be not good for a person who is not familiar with this region. But a person who is not familiar with this region, but with certain inputs, additional input, that what you need to do to reach to that point, that additional knowledge will be sufficient for getting or for improving the performance of that model. That is the prior knowledge, what we call that one prior knowledge. It may be developed with the help of same machine neural network model, or with the help of some set of analytical equations or other means. Overall accuracy increases and training patterns significantly reduces while incorporating that knowledge. Okay, here three works we have in case of that only that prior knowledge incorporation in the existing model that you can refer if you are interested. That same model structure with certain different number of input and output. This additional neuron is incorporated here in the hidden layer, that what we call that one prior knowledge input. In addition to that original behavior, we need to incorporate that reference points here, data corresponding to that coming out from this gallery to the FPS, to the library, to sorry, that NITS cafe, to admin building, to gate, to something like that. That points will be excited with that knowledge here. Then how to take that knowledge on that way, the two different ways is there. One is coarse model, some rough model, very rough model. It is not bound to take the accuracy, but it is having, if you have roughly trained a model corresponding to the same excitation and response, then ultimately this knowledge will be sufficient to improve the performance of this one for reduced amount of training patterns. Okay, then another way is to calculate in the form of difference method. Then prior knowledge input and difference method, these are two different approach used for incorporating the knowledge in the existing neural network model. Here this mathematics we can skip. Coming to that first example, that estimation of radiation characteristic of a slotted microstrip antenna using KBNN, that is, just see the model, this one, x1 y1 x2 y2 t n, that is corresponding to example 2, and this is the response. Okay, because you are having two dimensional response, dual resonance, dual gain, dual antenna efficiency, dual radiation efficiency. That's why two dimensional this one, and these 2 points are to be differentiated when we will have corresponding to gain, bandwidth or something. That's why one mod is also incorporated here. When we are getting values correspond this point equivalent to 1, then the response coming at these 2 points is dual resonance. If we are getting a values nearby to 2 here, then the response coming to these 2 points is gain 1 and gain 2, same directivity, antenna efficiency, radiation efficiency. Otherwise, it will be difficult to predict that response coming to these points is corresponding to what set of parameters. Okay, then input sides. Now 5 geometry parameters along with 4 different classes of slots: asymmetrical cross slot, square slot, longitudinal transverse slot. We need to differentiate that one. What dimension you are feeding between x1, x2, y2, x2, y2 and t, it is correspond to which slot, that is to be differentiated. The difference we incorporated here in the input side, that is 2 mod controls are additionally incorporated in that model to make the performance in a that way. Now this is the structure of that model. Activation function, 10 sig and log sig, mean square error, learning rate, momentum coefficient, training with LM algorithm, number of iterations, training time, required memory. Then coming to that performance, that in the difference method, the structure is optimized in this way, and to find model, the structure is this way. Then in PKI, prior knowledge input, the same patterns is followed. Now the algorithm for these two different cases is used. Now how the performance is coming like this. Standard ML model, the structure was 6 into 87 into 36 into 3. Now it is 2 models of less resource required. One is, this one is coarse model because it is having less neurons in the hidden. It is having more neurons in the hidden. That is the fine model. Okay. Then KBI, prior knowledge input. And the how the performance is, number of weights required for the traditional model is 37,762, and that in case of difference method and KBNN, the PKI method, that you can see how it is drastically reduced. Then resources, means computational resources required, is very small as compared to that earlier traditional one. Number of biases 126, 34, 30. Okay, here accuracy, number of weights are also, because this, if you calculate that one percentage reduction, it is only 8.085% required in difference method and 8.13% in PKI method. Number of biases is this one. Accuracy, when we take the traditional approach of 70% training, 30% testing, then ultimately just see the error. Standard MLP 5.83% error, 5.79%. In case of difference method, it is reasonably reduced one as compared to that one. In case of PKI method, now if you make a comparison of difference method and PKI method in this case is more accurate to the difference method. Coming to that one, 50%, 50%. training is 50%, testing with 50%, means what you are doing, you are going to reduce the training patterns and increasing the testing one. 30% to 50%, here 70% to 50%. Just see the change. Again, PKI method is better than to this one, difference method, and both the methods are more accurate rather than to the standard MLP model. Here 40% to 60%. Okay, then ultimately here just see this one, these two cases are more accurate. More accurate means requires lesser amount of training as well as testing infrastructure as compared to that standard MLP. And that error means MLP model, difference method, PKI method, number of testing patterns to the average testing error, that you can see that in both the cases it is very low as compared to that ML1 for 30%. Number of testing pattern 30%, then it is less when you are making testing pattern 40%. 40% testing pattern means 60% training pattern, and 50%, just see this one. Okay, here ultimately beyond that one again it starts to increase, that you need to have a trade-off, that up to what level you need to get the reduction in the error. Then same and average testing errors, number of patterns versus that. Coming to that last one quickly, in 5 minutes, less than 5 minutes it will take. Prediction of slot shape, slot size and inserted air gap of a microstrip antenna using say KBNN1. Here just see that S equivalent to out of 4, which is specific slot prediction. Z means position, where you are placing that one, X coordinate, Y coordinate of these two slots, and AG is the air gap. Then ultimately input side, electrical performance, dual resonance, dual frequency gain, dual frequency directivity, antenna efficiency, radiation efficiency. Then need to apply knowledge based approach to reduce the structure of this one, because we'll see that one, the same approach what we have used earlier, but the all values are different because it is optimized in case of this particular case. Just see this one, standard 10, 76, 78 by 6, number of weights, number of biases, and it is in these two cases. Number of weights, that is only 6%, 7.51% number of biases. Performance predicted and simulated and measured one, that you can see this one. Number of training testing sets 70, 30, 50, 50, 40, 60. Then ultimately here you can see that here difference method is more accurate to the PKI method. Okay, that can be discussed in case of that geometry, that how we have inserted that pattern. Okay, because of time constraint not possible to go into the detail, just an overview of that one. Then performance parameter, performance comparison, error comparison versus number of patterns. Here optimized values and predicted values. Coming to that one, that apart from that that power combiner and that power splitter, that analytical methods, numerical method that we have overviewed. Then simulation approach, two different example on traditional ANN, two different example on that one, your knowledge based one, and the reference for this one, that knowledge based, that you can take this reference, that is most recently published in 2023, that is computational intelligence for modeling and optimization of RFEH and WPT. It several cases of individual components, several cases of complete systems, that you can see in that review survey. Then here especially that machine learning approach for different cases, some references based on the work of our student here at NIT Silchar. Then the conferences last 2 years, then that is one patent which also published based on the work of one my student Debanjali. Then here ultimately one edited book was also published in December 2023, that is modeling and optimization of planar circuit using computational intelligence, different techniques, that comprehensive discussions on different approaches for modeling and optimization that we can see in this way. Apart from that, the students' contribution, these are the core funding agencies behind this work, especially in that DST as well as that SCRB under Vajra. Vajra is still going on. And last month, that Professor Sembiam Rangarajan from California State University has visited us. He stayed with us for 15 days. Earlier, like in January, he stayed with us for 1 month complete as, as per the part of this project. And with this one, like how this important approach, machine learning, not only that machine learning for modeling and optimization, that first time in the history of Nobel laureate that it was given in physics in 2024 based on the work on machine learning. That is last year Nobel laureate. Okay, with this one, conclude myself. Thank you.
Thank you very much. So it's time to open the question and comments. Do you have? Yes.
Sir, in KBNN modeling,
Yes.
we are giving enhancing knowledge to that
Yes, yes,
part prediction,
Yes.
that ANN type of network.
yes, yes,
So we should also program that
yes,
firstly,
yes,
and we are programming that roughly.
yes.
So it will
No, not programming. Programming approach will be same what you are going with the fine one. But that structure will be very rough, which is having more error. You need not to spend time to make it more accurate. Rough estimation will also be okay to
but
that one.
sometimes it can also give many errors or
Yes.
extra errors.
Yes, yes, yes. That is there.
Like in second approach, that
Yes. Yes,
difference
it
method
will
is-
always be. Because it totally depends on the behavior, what you are expecting from the simulation environment and how it is relating to that other sides.
but in a standard approach it is taking time.
Yes.
But in this
This
approach
number
we
of
are getting,
resources is required more.
yeah, so that's why it is taking time.
Yes.
But in this error we are getting errors
Which one?
in KBNN.
No. We are not. We are getting more accurate, more accuracy in
But
KBNN.
it can leads to error in error manner.
No, it up to 40, 60 on several cases we have tested, no problem at all. If you are going to further reduction below 40% in training, then drastically that you have seen one of the that it starts increasing after 60%. That KBNN errors is starts increasing. Just you can see that one. In last example, you can take this one up to 50 reasonable. If you are doing that one, then again it starts to increase, and very unpredictable performance you will get after 60%. Then it is fine up to this 30% to 60%, not beyond that.
Okay, but like as you given one example, like 2 plus 2 4 we are giving to a child.
Yes.
But if
Here that prior knowledge in this case may be 2 plus 2 equal to you are giving 3.9. Rough approximation, or 4.1 equivalent to. So that approximation, rough approximation is sufficient to.
so we are not giving him like a
2 plus
line
2 equal to
method
4.
which we
No,
are giving.
2 by 2 equal to 4. That's why that rough estimation is required. You are not defining the complete path from this room to that NIT point outside, giving certain points only. And you need to take that reference to improve the efficiency of that model.
Okay, thank you, sir.
Yes.
In one paper, you mentioned the resource consumption is 36 MB, something like that.
What?
In one slide, you mentioned the resource consumption is 36 MB.
6 MB.
Yeah.
Oh, RAM.
Yeah. RAM.
Yes.
So why not go for more resources? Like now we can afford GBs.
Yes.
So if
Why
we
not?
go,
We can go that one. That's why that further reduction or further extension usually comes.
so you can use like instead of limiting in MB,
Yes.
it can test in GBs and all.
Yes, it may be possible, no problem. That is the open for you to explore that one.
Okay.
That
So,
idea you can apply the what resources are available presently.
so this 36 MB is a choice or like,
Limitation, not choice.
I mean, did like in paper, did you like try to limit the RAM usage or like it is?
You just see that one. That starting part of that one, maybe this one or earlier KBNN was during my PhD. That time
Okay.
we are having rarely
Okay.
4 MB RAM. Now you can think about 16 GB and even 32 beyond that one.
Okay.
Okay, that was the what resources are available to you. You need to take that reference. Maybe next 10 years the resources will be very advanced, easily available in the laboratory.
Okay.
Okay.
Anyone? No? So it's
Okay.
just in time. So thank you so much.
Yes. Thank you.
So it's tea break time, and please go back here 10 minutes later. So 11:10.
Yes.